All right, welcome back to the deep dive. Today we're taking a look at something that's pretty fundamental to how our computers work these days, and that is PCIe.
Yeah, PCIe. It's
Yeah.
like the central nervous system of a modern computer, right? It's how all the crucial components talk to each other. Your graphics card, your SSD, your network card, even things like sound cards, all that data zipping around at insane speeds.
And it just keeps getting faster, too. We've
Yeah,
got PCIe 6.0 on the horizon, and the bandwidth numbers are just mind-boggling.
absolutely. We're talking potentially 64 gigatransfers per second per lane. That's what, 8 gigabytes per second? Just on a single lane.
It's unbelievable. And obviously, with all that data flying around, you need some seriously clever ways to manage it all, right?
You got it. And that's exactly what we're diving into today, a relatively new feature called Deferrable Memory Write, DMWR for short. It's a way to handle memory write operations much more efficiently in this super high-speed environment. And it's showing up in both the latest PCIe 6.0 spec and in CXL 1.1.
DMWR, Deferrable Memory Write. Okay, so from the name, it sounds like it's giving the system a way to, postpone actually writing something to memory. Sort of like hitting a pause button on that process. But why would you want to do that? Wouldn't that just slow things down?
Yeah, that's a great question. The why here is really the key. The thing is, this pause button is actually a bit of a speed booster in disguise. To see how, we need to dig a little deeper into how PCIe works, the language it speaks. Specifically, DMWR is a new kind of transaction layer packet, or TLP.
Okay, TLP, transaction layer packet. Remind me, what are those again?
Think of them like the envelopes that carry data and instructions over that PCI highway. You've got different types for different purposes, right? Some are for reading data, some for writing, some for configuration, and so on.
Right, right.
Now, the crucial thing about this DMWR TLP is that it's categorized as a non-posted request, or NPR for short. And that distinction is really important here.
Non-posted. Okay, I vaguely remember that term, but refresh my memory. What does that actually mean, and why is it such a big deal for DMWR?
Sure. Imagine sending an email, right? Just a regular email. You hit send, it goes off. And you don't necessarily get a direct confirmation that the other person actually opened and read it. That's like a posted request.
Okay, I'm with you.
But then imagine sending, say, a certified letter, something that requires a signature upon delivery. That's more like a non-posted request. You need that confirmation, that signature, to know that the recipient actually got it. And in the PCIe world, that confirmation comes in the form of a completion TLP.
Ah, I see. So it's like the receiver is signing for that data package, basically saying, yep, I got it.
Exactly. So with your standard memory write, the MWR type, that's like our regular email, posted, no confirmation needed. But then you have other types of non-posted writes. For example, when the system needs to talk to a device's input-output ports, or when it needs to configure a PCIe device. Those get a confirmation, and usually the expectation is that the receiver acts on it pretty much immediately.
Right, right. Makes sense. So where does this DMWR fit into all of this?
Well, the really clever thing about DMWR is this. It is non-posted, so it does need that certified letter confirmation. But it also gives the receiver, the one we call the completer, the option to actually delay the actual writing of that data to memory.
So it gets the confirmation, but it can sort of sit on that data for a bit before actually committing it to memory.
Precisely. That's the key difference.
Yeah.
And that ability to defer, to use that pause button you mentioned earlier, is the whole point of DMWR. It introduces this new level of flexibility into how the system handles memory write requests.
Okay, so it's not just blindly writing everything to memory as soon as it gets it. It has the option to say, hold on, let me deal with this later.
Yeah.
But how does that actually translate into better performance? What are the benefits of being able to defer these writes?
Well, there are several. One big advantage is that it can simplify flow control.
Flow control, right. That's how the system manages the flow of data between different components, making sure nothing gets overwhelmed.
Right. In a traditional setup, the receiver basically tells the sender how much space it has available in its buffer, and the sender has to keep track of that and make sure it doesn't send too much at once. But with DMWR, the receiver gets this extra tool. It can acknowledge a write request right away, but then decide to delay the actual write if it knows things are about to get congested.
So it's like having a traffic cop who can say, hold back for a second, let this other lane clear up a bit.
Exactly. It's a much more nuanced way of managing the flow of data. And that can lead to reduced latency, especially for time-sensitive operations, and it can potentially boost the overall throughput of the system. Basically, it lets the system manage its resources more intelligently.
So instead of just slamming on the brakes when things get full, it can kind of smooth out the flow a bit more.
Exactly. And that's just one of the benefits. There's also the potential for better utilization of system resources, like memory bandwidth, and even a reduction in CPU overhead, since other devices might be able to handle their write operations more autonomously.
Okay, this is starting to make a lot of sense. So let's walk through a real example. How would a DMWR transaction actually play out in, say, a typical system?
Sure. Let's say your network card, which is super fast these days, needs to store some data in the system memory, which is managed by your CPU. The network card is our requester here, and the CPU is the completer. So the network card starts by sending a DMWR TLP over the PCIe link, basically saying, here's some data, please store this for me.
And what happens on the CPU side?
Almost immediately, the CPU sends back that certified letter confirmation, the completion TLP. That tells the network card, yep, got your request loud and clear.
Yeah.
But here's where it gets interesting. Now the CPU has a choice. It can either go ahead and write that data to memory right away, or it can choose to defer it, to hit that pause button. And this isn't automatic. It's a decision made on a case-by-case basis.
So what kinds of things factor into that decision? How does the CPU decide whether to write now or later?
Well, a big factor is the current load on the memory system. If there's already a ton of traffic going on, other devices trying to read or write data, it might make sense to postpone that write. It's also about the priority of other transactions. Maybe there's a request to read some really crucial data that needs to happen right this second. Or maybe the CPU itself is just super busy with other tasks and doesn't want to be bogged down with managing this right now.
So it's about juggling all these different demands and figuring out the most efficient way to handle everything. So let's say the CPU decides, yep, going to defer this one. What happens on the network card side? Does it just wait around?
No, not really. Remember, it got that initial confirmation, that completion TLP. So as far as the PCIe protocol is concerned, its part of the transaction is done. The network card knows the CPU got the request and will handle it eventually.
So it can go about its business and not worry about it anymore.
Right. Meanwhile, the CPU will keep an eye on things, and at some point when it makes sense, maybe when memory traffic dies down a bit or it has a spare moment, it'll actually perform that deferred write. The key is that the CPU now has control over the timing of that write. It can optimize things based on all these other factors going on in the system.
I see. So the CPU becomes sort of a traffic manager, making sure things flow smoothly.
Exactly. And this really ties back into what we were saying about flow control. You see, with traditional flow control, it's all about the receiver saying, I've got this much space left, send me data. But with DMWR, it gets this extra lever. Even if it does have space, it can still choose to delay a write if it anticipates a bottleneck or wants to prioritize other things.
Right. It's not just about how much space there is, but also about when is the best time to actually use that space. It gets a lot more strategic.
Exactly. And we actually see hints of this kind of thinking in some real-world designs. For example, some Intel FPGAs might be designed to accept a huge number of non-posted data packets. But then they'll use header information, along with DMWR, to actually manage that overall traffic in a much more refined way.
So it's like having both the green light and the ability to say, hey, yield for a sec.
Yeah.
It's a lot more flexible.
Precisely. And this kind of approach can be really powerful. So where are we likely to see DMWR actually being used?
Yeah, what kinds of real-world applications will benefit from this?
Well, one area where it's likely to be really valuable is in scenarios involving what are called shared work queues. Imagine you have multiple processors or devices that all need to send commands or data to some central unit. Without DMWR, you might need dedicated hardware logic to manage each of those incoming streams. But DMWR lets multiple requesters submit their requests without blocking each other. The fact that the completer sends back that acknowledgement after receiving the DMWR, even if it's deferring the actual write, is a really efficient way to signal that the request has been accepted and will be handled eventually.
So it's like streamlining those interactions, making sure everyone's on the same page without creating a bottleneck.
Exactly. And beyond that, it has applications in a whole range of areas. High-performance computing and data centers are big ones, where you have massive amounts of data constantly moving between CPUs, GPUs, storage, and specialized accelerators. Being able to optimize the timing of memory writes can lead to big gains in those environments.
Right, those systems were all about squeezing every last bit of performance out of the hardware. So DMWR seems like a natural fit there.
Definitely. And then there's artificial intelligence and machine learning. Those fields rely on processing huge data sets. And DMWR can make a big difference in how efficiently that data is moved around and processed. Even the automotive industry is starting to see the potential benefits. As driver assistance systems and infotainment systems get more sophisticated, they're handling more and more data in real time. DMWR can help ensure that data is exchanged between processing units and memory in a really reliable and efficient way.
It's amazing to think about how this one feature, DMWR, could have such a wide-ranging impact across so many different areas. And I'm guessing there are even more applications we haven't even thought of yet.
Absolutely. It's a really versatile tool. So let's talk a bit more about the specific benefits. We've touched on some of them, but it's worth summarizing the key advantages.
Yeah, let's break it down for our listeners. What are the main takeaways in terms of how DMWR can actually make our computers faster and more efficient?
All right. So first and foremost, reduced latency. By allowing the system to prioritize critical operations and postpone less urgent ones, it can make the whole system feel snappier and more responsive. Then there's the improved efficiency in how system resources are used. Memory bandwidth, in particular, can be managed much more effectively by grouping or scheduling writes to happen during periods of low congestion.
Right, sort of like smoothing out the flow of traffic instead of having everyone try to merge at the same time.
Exactly. And this could also lead to a decrease in the load on the main CPU, since other devices might be able to handle their own write operations more independently. And all of this can ultimately lead to an increase in overall system throughput.
So it's about making the whole system work smarter, not harder.
Precisely. And it can also help reduce contention in those situations where multiple devices are all trying to access the same shared resources at the same time.
Okay, we have a table here in our notes that compares the different types of PCIe memory writes. Can you walk us through that, maybe highlight how DMWR stands out from the others?
Sure. So you've got your basic memory write, MWR SAR, that's a posted request, so no confirmation needed. And it doesn't allow for deferral. It's a straightforward write this to memory operation. Then you have IO write, IOWR, and configuration write. Those are both non-posted, so they do require confirmation. But they also don't allow for deferral. The expectation is a pretty immediate action. And then you have DMWR. It's also non-posted, needs that confirmation. But the key difference is that it does allow for deferral. That's what sets it apart.
So it's non-posted, like those other two, but it adds that extra layer of flexibility with the deferral option.
Exactly. That's what makes it so powerful. But, there's always a trade-off, right?
Right. No free lunch in engineering. So what are the downsides? What makes DMWR tricky to implement?
Well, one of the biggest challenges is that it introduces a whole new level of complexity when it comes to timing. You can't just defer those writes indefinitely. They have to be completed within a certain time frame to avoid problems like timeouts, where the system basically gives up waiting for the write to finish. And that makes synchronization between the sender and receiver even more critical. You have to be absolutely sure that data isn't lost or corrupted because of those delays.
So it's not just a matter of throwing in a pause button. You have to make sure the whole system is carefully coordinated.
Exactly. And of course, making sure that a device actually implements DMWR correctly according to the PCIe 6.0 specs or the CXL specs adds another layer of engineering challenge.
Right. It's not just about the concept, it's about getting the details right. And how about testing? How do you even verify that DMWR is working properly when the timing of operations is now, well, potentially all over the place?
That's a great point. Verification becomes a lot more complicated. You have to do your standard functional verification, making sure that both sides of the connection are implementing DMWR correctly and that it follows all the rules. But then you also have to verify the performance optimization. Just because DMWR can improve performance doesn't mean it automatically will in every scenario. You need to run rigorous tests under different workloads to actually measure and validate the real-world impact. And then there's error handling. You need to make sure the system can gracefully handle any errors that might crop up, specifically because of these deferred transactions, like those timeout issues we talked about.
So it's not just about making it work, it's about making sure it works well and that it can handle anything unexpected that might happen.
Precisely. And to really see the trade-offs here, we have another table in our notes that lists the benefits and challenges side by side. It really highlights the fact that while the potential gains are huge, actually implementing DMWR correctly is no small feat.
It's like any powerful tool. You have to use it wisely and carefully to really reap the benefits.
Exactly. So one last question about DMWR and its place in the PCIe world. It's part of the PCIe 6.0 spec. But does that mean every device that claims to be PCIe 6.0 compatible has to support it? Or is it more of an optional thing?
Yeah, that's a good question. I'm curious about that too. Because not every PCIe device needs to be a speed demon, right?
Right. And from what we've seen, it seems like DMWR support is likely going to be optional for PCIe 6.0 devices. The spec actually mentions that a system should check if a device supports DMWR before trying to use it. That strongly suggests that it's not a mandatory feature.
So it's more of a if you need it, you can use it kind of thing.
Exactly. And the fact that there's a specific extended capability defined for DMWR support also points to its optional nature. These extended capabilities are typically used for things that go above and beyond the core functionalities of the standard.
So if a device does want to support DMWR, what does it actually need to do? What are the key implementation requirements?
Well, the main thing is that it needs to implement what's called the DMWR completer capability. That basically means it's equipped to handle incoming DMWR requests. And if those transactions need to go through any PCIe switches in the system, those switches also need to be designed to handle DMWR traffic correctly.
So it's not just a matter of flipping a switch. There's some actual engineering work involved in making sure the hardware can handle it properly.
Right. And ultimately, whether a device manufacturer decides to include DMWR support will probably depend on the specific applications they have in mind. If the potential performance benefits are really crucial, then it'll be worth the extra effort.
Makes sense. So to wrap things up, can we just do a quick recap of the key points about DMWR, just to make sure everyone's on the same page?
Absolutely. So DMWR, deferrable memory write, is this new type of memory write operation introduced in PCIe 6.0 and also in CXL. The big idea is that it allows the receiver of a write request to acknowledge that request right away, but then actually defer the writing of the data to memory until a later time.
And that gives the system a whole new level of flexibility in how it manages memory traffic. It's about making things more efficient and preventing bottlenecks.
Exactly. And that can lead to faster processing, reduced latency, better utilization of system resources, and a bunch of other benefits.
But it also comes with some challenges, right? Primarily around managing the timing and synchronization of all these operations and making sure everything is tested and verified thoroughly.
Right. It's a powerful tool, but it's not a magic bullet. It needs to be implemented carefully and strategically to really unlock its full potential.
Well, I'd say this has been a truly deep dive into the world of DMWR. I feel like I've learned a lot, and hopefully our listeners have too. And on that note, here's a final thought for you to ponder. We've been talking about DMWR in the context of computer hardware, but the concept of strategically prioritizing and deferring tasks is actually applicable to a lot of things in life. Think about how you manage your own to-do list, or how a complex organization like a hospital or a manufacturing plant operates. Often, the key to efficiency is figuring out which tasks are the most important, and then finding ways to defer or delegate the less urgent ones. So maybe, just maybe, understanding the principles behind DMWR can give you a fresh perspective on how to manage your own time and resources more effectively. And that's something to think about. Thanks for joining us.